Alright, welcome to the last video of our class. This is going to do the geometric series, which is going to take a geometric sequence and add it up. And so if it's finite, it's going to have a fixed number of terms and therefore have a fixed value. If it's infinite, it could be that the geometric sequence actually still obtains a value, and sometimes it will be like the arithmetic where it just goes to infinity or to negative infinity as the case may be. If the sequence is geometric, um, then its addition will be a geometric series. So we're going to find the sum of a geometric series. So here's a geometric series where 2 is being multiplied every time, this very first one. And so we get a nice 62 as we add that. Here's the sum of the first 5 powers of 3. Notice 3 is being multiplied every time for 363. Here's the general formula for a finite number of things being added, the first n terms. It's a little bit crazy, but still manageable, usually best done with a calculator depending upon what r is. But it gets big. So if we watch that formula in action, so what it says is take the first term and then multiply it by 1 minus the common ratio to the nth power all over 1 minus r. So you're going to need to know the first term and the number of terms that are there. So if we want to add the first 12 terms of this series right here, first of all, we need to see if it's arithmetic, geometric, or something different. In this case, it looks like 2 is being multiplied every time. Times 2 gets me to the next one. So the common ratio is 2. We start out as 4, and we have 12 things. And so we're just dropping those things into the formula. If we want the sum of the first 12 numbers, we have our a1, which is 4. 2 goes in for r. And then we put those guys together. If a calculator is not allowed, we'll allow you to use a calculator. You can give me a calculator answer of 16,380, right? Because you have that. But if it's not allowed, you're welcome just to leave it in its exponent form. So nothing earth-shattering, we're just using that formula there. So again, here we're going to recognize, oh, negative 3 is being multiplied every time. And so we're going to drop a negative 3 in there. And we're looking for the first 27 terms because that's what they asked for. And so we're just dropping it in, clearing up as much as we can, and then using a calculator. The calculator is going to sometimes have an issue. Leaving the answer in exponential form gives the exact answer. So I guess leave it in exponential form. See what he's doing in the homework. But if you want to get a rough idea of what it is, it's huge because they get big and get big quick. So if you go 27 terms out, it's big. Notice here the common ratio, everything's being halved. So the common ratio is 1/2. They're asking for 10 terms. We drop that in to its right position. We drop the, not sure why he wrote 1/3 there, it's 1/2. We drop the 1/2 in to its positions, and then the rest is stagnant, with the exception of A1 being 16 has a position, but those ones are stagnant in there. And then you end up simplifying as much as possible, right? Don't leave it as a complex fraction. We're asking you to leave it in exponential form, but not crazy form. So you got to get that 1/2 up, and so that makes that a 32. Example 4 wants you to find the sum of this series right here. And so we're looking at that, and we have to decide, is that geometric or not? And so it's not bad to just put out the first few terms and realize, oh yeah, it's multiplying by 3 every time. We'll start to see that that's the common ratio. So common ratio is 3, first term is 4, and so therefore we're going to run this through and just drop numbers in and come up with a nice exponential form, which you could put, if you'd like, in a, what do you call it, in a decimal type of form, expanded form. So an infinite series can be written as a1 geometric series, a1 plus a1 times r plus a1 r squared, right, using the recursive definition. And it's going to go on forever. That's why it's infinite. And so they'll utilize this infinity symbol. Can you find the sum of a geometric series if there's infinite number of terms? And the answer is yes, but it depends on the common ratio of r. So if r is between -1 and 1, right? If the absolute value of r is less than 1, if we have a true fraction, then they'll have an exact sum, because what's happening there is it's tailing off to nothing. And at some point you're adding on such a small amount that the limit value is a particular value that's coming out. And it's going to do what they say converges, right? So notice that's if r is less than 1, it's going to converge. And here's the sum of it. Very easy, actually. a1 divided by 1 minus r. If the geometric series does not converge, then we say it diverges. And divergence just means it goes off to infinity. So take a look here. This is definitely a converging geometric series because r is 1/2. So what is it going to limit out to? 1 over 1 minus 1/2, or 2. All that's going to add up to be 2. And yes, you're adding, 1/32, 1/64, 1/128, 1/256, 1 over 512. But it's adding such a small amount each time that it's underneath 2 and getting closer and closer to 2. So the result says the total infinite number of fractions is exactly 2. The partial sums gets closer and closer to 2, but the sum of the exact term is of infinite number terms is exactly 2. And so this concept will be explained further in your calculus class, and it will, right? And so he's showing what the sum of the first 7 terms are. Look, you're already really close to 2 at the 7th term, but you'll never be at the 2 no matter where you looked previous, and it's converging to 2. It's getting closer and closer. 2/3. 2/3 is the ratio here. It's way less than, well, I shouldn't say it's way less. It's less than 1, and so it's going to converge, and you just drop the 2/3 in. Remember, this is the formula. You're welcome to have it with you, and you just drop that in and watch it go. Example 3, the 1/3. You're going to put the 1/3 in there, respecting the first value as being 9. And do your work, do your magic there, and come up with 14.5. And then r could be negative and converges. And so you drop in the -1 and you come up with a nice 2/3 out of that. Hopefully you're seeing that okay. Let's take a look. There's a little mistake here. This right here should be a 1. Not sure how a1 was 1. And 1 minus 1/2. He has that corrected here. So 1 over 1. Yeah, you can see that you get 3 halves there, 2/3, and we get a nice 2/3 out of that. And so just a summary, if r is greater than 1, then it's going to be increasing without bound and therefore going to be divergent. If it's between 0 and 1 but positive, it's going to decrease and converge. If it's between 0 and 1 and negative, it's alternating, but it's also going to converge. And if it's less than -1, it's going to alternate but diverge, because the numbers are going to get as big as you need them to be. And so you'll keep that in mind in future classes. For now, he's just pointing it out, but just kind of informational only. But this should give you a nice introduction to sequences and series that should serve you well as a springboard into your next class when it's brought up.